They look up at the night sky. On a clear night, you'll see countless stars twinkling above. Each one of those stars is a giant ball of burning gas, just like our own sun. These celestial furnaces light up the universe and play a crucial role in its evolution, but stars like us have a life cycle. They're born, they live, and they eventually die. For some stars, their death is nothing short of spectacular, a brilliant cosmic explosion that we call a supernova. Supernovae are among the most violent and energetic events in the universe. They are so bright that they can outshine entire galaxies for a brief period. But these explosions are more than just dazzling light shows. They are the universe's way of recycling matter, forging new elements and shaping the cosmos as we know it. Understanding how stars end their lives in these spectacular explosions gives us a glimpse into the very building blocks of the universe and our place within it. Stars are born in vast clouds of gas and dust scattered throughout galaxies. These clouds, known as nebulae, are like cosmic nurseries where gravity gently nudges particles together. As more and more matter clumps together, the gravitational pull intensifies, drawing in even more gas and dust. This process generates heat, and the core of the collapsing cloud begins to heat up. Over millions of years, the core of this collapsing cloud becomes incredibly hot and dense. The temperature and pressure rise to a point where hydrogen atoms, the most abundant element in the universe, begin to fuse together. This fusion process releases an immense amount of energy in the form of light and heat, marking the birth of a star. Once a star ignites nuclear fusion in its core, it enters a long, stable period known as the main sequence. This stage constitutes the majority of a star's lifespan. During this phase, the outward pressure from nuclear fusion balances the inward pull of gravity, creating a state of equilibrium. Our own sun, a yellow dwarf star, is currently in its main sequence, about halfway through its estimated 10 billion year lifespan. The length of a star's main sequence depends on its mass. Massive stars burn through their hydrogen fuel much faster than smaller stars. While our sun will shine for billions of years, a star 10 times more massive might only live for a few tens of millions of years. This difference in lifespan plays a crucial role in determining how a star will eventually die. A star's life is a constant battle against gravity. The outward pressure from nuclear fusion in the core prevents the star from collapsing under its own weight. However, like any fire, a star's nuclear furnace eventually runs out of fuel. When a star begins to exhaust its supply of hydrogen, it marks the beginning of the end of its life cycle. As hydrogen in the core depletes, the outward pressure decreases and gravity begins to gain the upper hand. The core contracts and heats up even further, becoming hot enough to fuse helium, the byproduct of hydrogen fusion, into heavier elements like carbon and oxygen. This process releases even more energy, causing the star's outer layers to expand significantly. The star swells up into a red giant hundreds of times larger than its original size. Section 5. The death of giants, supernova explosions. The fate of a star at this point depends on its mass. Smaller stars like our sun will eventually shed their outer layers, leaving behind a dense, hot core called a white dwarf. These stellar remnants slowly cool over billions of years, fading away into obscurity. However, for massive stars, the end is far more dramatic. Massive stars continue to fuse heavier and heavier elements in their cores, creating elements like neon, magnesium, silicon, and iron. However, fusing iron requires more energy than it produces. This creates an imbalance, and the core can no longer support the weight of the star's outer layers. The core collapses in a fraction of a second, triggering a shockwave that rips through the star, resulting in a cataclysmic explosion known as a supernova. Section 6. Type 1 supernova, cosmic fireworks. There are two main types of supernovae, each with a different origin story. Type 1 supernovae occur in binary star systems where two stars orbit each other. One of the stars is a white dwarf, the dense remnant of a sun-like star. The white dwarf's intense gravity pulls material from its companion star, accumulating it on its surface. As the white dwarf accumulates more and more material, its mass eventually reaches a critical point known as the Chandrasekhar limit. At this point, the white dwarf becomes unstable and undergoes a runaway nuclear fusion reaction. igniting the entire star in a brilliant explosion. Type Ia supernovae are remarkably consistent in their brightness, making them useful tools for measuring cosmic distances. Type II supernova occur at the end of a massive star's life, as we discussed earlier. When the iron core of a massive star can no longer support its own weight, it collapses, triggering a shockwave that tears the star apart. Unlike Type Ia supernovae, which are fueled by runaway nuclear fusion, Type II supernovae are powered by the gravitational collapse of the star's core. This core collapse compresses the core into an incredibly dense object, either a neutron star or a black hole, depending on the original mass of the star. Neutron stars are incredibly dense objects, packing the mass of the Sun into a sphere only a few miles across. Black holes are even stranger, regions of space-time where gravity is so strong that nothing, not even light, can escape. Supernova explosions are destructive events on a grand scale, but they also play a crucial role in the universe's evolution. The intense energy released during a supernova forges heavy elements like gold, platinum, and uranium, which are scattered throughout space by the explosion. These elements are the building blocks of planets, moons, and even life itself. The expanding shockwave from a supernova can also trigger the formation of new stars. As the shockwave compresses nearby clouds of gas and dust, it can initiate gravitational collapse, leading to the birth of a new generation of stars. In this way, supernovae play a vital role in the ongoing cycle of stellar birth and death in the universe. Supernovae are not just spectacular events, they are the universe's grand recyclers. The elements forged in the hearts of dying stars are scattered throughout space, seeding the cosmos with the building blocks of planets, stars, and life. Every atom in our bodies, from the iron in our blood to the calcium in our bones, was once forged in the heart of a star that died billions of years ago. These explosions also enrich the interstellar medium, the vast clouds of gas and dust that fill the space between stars. This enriched material will eventually collapse to form new stars and planetary systems, continuing the cycle of cosmic evolution. In a very real sense, we are all stardust, formed from the remnants of long-dead stars. Studying supernovae provides us with invaluable insights into the fundamental laws of physics and the evolution of the universe. By observing these distant explosions, we can learn about the life cycle of stars, the creation of heavy elements, and the expansion rate of the universe. Supernovae are powerful beacons that illuminate the distant cosmos, allowing us to probe the vastness of space and time. Their study continues to challenge our understanding of the universe and inspire us to unravel the mysteries of the cosmos. As we continue to explore and understand these spectacular explosions, we gain a deeper appreciation for the interconnectedness of the universe and our place within its grand cosmic dance.